It's recording at the moment.
So on Friday I was recording stuff and it kept shutting off. And I thought, am I accidentally hitting something? And then one of the times I was not touching any buttons. I just had the thing in my hand and it stopped recording. So I'm recording the lectures until the phone decides not to. So let's see. Today's the 14th?
Yes.
Okay. So Quetzal chapter 3 on Wednesday. Any questions on, I believe Naveen, you had a question on something?
In phonetics, the question about the time to reach to the opposite shore.
Okay.
I don't understand how to determine the time. What is the relationship between the time and the speed? How is the faster, not the shorter time?
All right, so when you are dealing with motion, so for instance, you have the two components of velocity. And again, this is problem 46 from chapter 3. This is how fast the river is going, and this is how fast and the direction the person is actually rowing. So the actual velocity of the person, well, you add these two vectors together, and so that's the actual velocity that they're traveling. But when it comes to getting to the other side, this part right here is not affecting how fast it takes to get across. That it's completely how much of the velocity is directly in that direction. And so when looking at that, and you have to base it upon the drawing, the question is which of the arrows is pointing the farthest to the right? And that would be the middle one. Even though that's not the fastest he's traveling, that is the fastest in that direction. So, is that sufficient or?
Yeah.
Okay. Any other questions at this point? Have any of you ever dealt with a singing mask? Okay. I'm just wondering how effective they were. All right, in the absence of other questions, let's talk about friction. As I'm sure all of you have just been waiting for all weekend long. So near the end of the last thing we did, we had two formulas here. That the static friction is less than or equal to this coefficient times the normal force. So the normal force is an indication of how tightly two things are pressed together. It's actually the force that keeps one object from going through another. But the larger the normal force, the more tightly two things are pressed together. And mu s here, again, u sub s, is the coefficient of static friction. And that is completely dependent upon the surfaces. And then we also had that the kinetic friction is equal to mu sub k times y. Where again, y is the normal force. It's the force that keeps two objects from going through each other. And mu sub k is the coefficient of kinetic friction. where kinetic, as usual, means movement, and this specifically, one object moving relative to the object it's touching. So let's just do a quick little experiment here, where we actually find the kinetic friction between the book and the table. So what I need to do is figure out, I'm going to have this thing slide, I need to figure out how far it's actually going to slide. So let me grab a meter stick. And it's going to hit the tape. And if I take the tape, we'll do it off to this edge over here. There we go. So if the far edge is right on the edge of the table, then the mark is right there. And we need a finish line. So the book's going to slide a meter, so when the leading edge hits this tape, that's a meter. All right, so we have a meter marked out, so the book's going to slide from here to here. What we need to do is time how long it takes. So if you have your phone with a stopwatch on it, I'd appreciate it if you get ready to do timing. I'm going to lift up this edge of the table, keep the book in place, and then I'm going to do something clever like 3, 2, 1, go. When I say go, I'm going to let go of the book. Book's going to slide down to the end, and then you stop timing when the book touches the tape.
The bottom edge of the book?
Bottom edge of the book.
Okay.
And I'm going to do one other thing. Get rid of some of the residue to try to at least have an even surface all the way down. So I need to lift the table. And how is this going to work? Not well. Wow. Right now, there's static friction acting on the book because the book is not sliding. Get it going. So notice it didn't move at all, and then once we hit that breaking point, it started sliding. Barely. I would like it so I don't have to tap on it. All I have to do is just let go. Surely that's enough. Wow.
The chair's sliding. The chair's sliding.
It is. We can do that kinetic friction. Let's see. Oh, how about if I just move it farther under? Is the chair moving at all?
No.
Okay. Thank you. All right, here we go. And then to the clever 3, 2, 1, and so on. All right, here we go. Both ready? 3, 2, 1, go. And before the whole thing goes caving in. Thank you very much. And for the camera, what we did is we tilted the table way up, put the book on it, timed how long it takes to go a meter. So the times.
90
90,
seconds
90 seconds,
or 90
or 0.9?
point. Yes.
Anyone else?
I got 0.95.
I got 0.99.
Okay, 0.98.
Oh. Carrie, I thought you said 0.9.
Oh.
You had 2 phones? Oh, you were 0.9. Oh. Your ventriloquism act is working really well. Any other times?
I stopped mine a little bit late, so I don't think it's accurate.
Okay. All right, we'll go with this. Averaging it, let's see. 2. Okay. All right, so that's how long it took. We do need to do one other thing. Dang it. We need to know the angle. Obviously, we should have done this earlier. I should have done this earlier, but good thing I'm not filling that part. Let's do the timing again. Let's just do it right. All right, so first the angle. Just working on your intuitive sense, what angle would you guess this is?
Mm.
170
Oh, I was thinking first quadrant angles.
from my perspective.
So 10 degrees from the horizontal?
Yes. Well, actually, exactly.
Maybe 30? 30?
Okay, got a 30 here.
Yeah, 30 horizontal. Yeah, that sounds about right.
Anyone else?
You got like 35.
Got a 35, all right, so you're here 30, you're here 30, 35? You moving to 35? All right, we'll leave it at that. 29, so congratulations, you two. So I have the table at a 29-degree angle. Let's do the timing one more time. All right, so we'll go. All right. Here we go. 3, 2, 1, go. Maybe those who said 35 were participating. All right, new angle. No, the people who said 35 were not anticipating, the people who said 30 were anticipating. All right, so we tipped it up with an extra degree. 30 degrees. That potentially makes the math a lot easier. In case there's something on the book. All right, here we go. 3, 2, 1, go. Guess I've done this like this too many times. Thank you. Got it. All right. Here we go. What are the times?
1.20.
1.20.
1.99.
Point.
99.
0.99.
0.96.
I got 170.
1.02. 1.02.
Anyone else? All right. Now we do seem to have a cluster here, and then the one that's out of it, which doesn't necessarily mean that's not right. But sometimes when you're faced with data like this, you do the average generally to eliminate some extremes. Or another thing you could do is just eliminate the top and bottom one and go with that. But let's stick with all 5 of them for right now. What average?
1.034.
1.034. All right. So we have the time that it took to go 1 meter. From this, we can find acceleration. I know that for something traveling in one direction at a constant acceleration, which we are assuming, so assume acceleration is constant. I know that the initial speed was 0 meters per second. And so we have our formula that the distance traveled is 1/2 AT squared. Or we could put vector symbols over it. It's, again, just traveling in one direction, so it works also if the vector symbols are not there. So this is 1 meter is equal to 1/2 times acceleration times 1.034 squared. So what is 1.034 squared? Feeling confident it's 1 point something.
It's 1.069156.
0.069
156.
And then times 1/2. 0.5345778.
Yeah.
All right, oops. What are the units?
If by
Oh, wait, sorry, I wrote that down wrong. That's 1 meter is equal to A times. All right, so what are the units of this?
second,
You're close.
it's a time.
Second squared. All right, so now the acceleration, therefore, well, the math problem is 0.5345788 equals 1. That's the math problem. And so the acceleration, well, divide by that 0.5345788. And it's going to be a little bit under 2, so 1.9 something. 0.95.
I got 1.87.
87. Units?
Meters per second squared.
Yep. Don't suppose I've written it in here already. I have not. All right, so we now need to know the mass of the book. Because I know the total force is equal to mass times acceleration. Newton's second law of motion. We now have the acceleration. We need to figure out the mass so we can figure out what the total force is. So we'll go to the handy dandy triple beam balance. All those are on 0. And it is more than 600 grams. And so our other choice is we have the electronic balance that's usually over here. That's a triple beam over there. Like I said, it's gotten moved. All right. So what I'm going to do, it turns out actually that the mass doesn't matter, but for the sake of what we're doing, actually finding the mass, I'll use two triple beam balances. That's and it's over 1,000 kilograms. All right, so since the mass doesn't matter, I'm going to make up a number. Assume mass is, we'll just say 2 kilograms. Ooh, actually, 2. That's 1. There we go, 2 kilograms. Who has a good sense of balancing, being able to feel these two things and know which, if one is heavier than the other? No one has a good sense for that.
Oh, this is heavier.
That is, all right. Hold that thought. Science in action. Here's 1. In case I need it. That's still heavier?
Yeah. It's getting close. Is it the same?
All right. We will assume it is, and for some reason the balance didn't care. Because that's oh. That should be the same as this one.
Yeah, that's what I'm like, is that the same as that?
There you go, that one's smaller. Which one's the lighter?
This is lighter.
Okay, so it's more than 500. It was more than 600. Apparently the two balance method was a horrible method. So let's change the mass to .7 kilograms. So now we can find the total force acting on the book. So I have our 0.7 kilograms times our acceleration of 1.87 meters per second squared. And we get a total force of
309.
309 units. Or you could also done kilogram meters per second squared, but Newton is the easy one. All right, so we now have the force there. And what can we get rid of? Let's get rid of this stuff. So at this point, if we had trig under our belt, there's a very simple analytic way of doing it, but we don't have that, so we're going to do this graphically. So what I need to do is establish 0 degrees. I'm going to basically draw my 30-degree angle.
I think I multiplied that wrong, I'm sorry. No, I'm right, I put the decimal in the wrong place, sorry.
Okay? Is that parallel?
No,
Which side goes up or down?
left, low.
Left goes up?
Mm-hmm. Back down a little
Little
bit,
down.
down a little more. Pretty close.
Was that last thing you said, Karen?
Well, it's pretty close.
Okay. We're gonna settle for close. So that's gonna be my starting point right there. This is 0 degrees over this way, 180 degrees over here. Let's think about this. We have, basically, this is box on ramp. That's the problem we're working with here. Got ramp, got book on sloped table. This angle here we have is 30 degrees. What are the forces acting on the book? We have our checklist, F down.
Weight, gravity,
Our weight,
gravity from the box go down to ground.
all right, your hand gesture was a little bit different than what I was expecting. Which way does weight act on it?
Like this,
Ooh.
go down. Yeah.
Weight is always,
Yes, yes.
all right, so I have weight acting down like that, okay?
From the ground,
Up,
acting
alright.
up,
Ground up.
then,
Let's go ahead and make the ramp part of the ground. All right, so weight was acting up.
then normal force,
Acting which way on what?
like this by angle. Normal, yes. The other one go down by angle. Then there is friction. Go up, yes. From the ground go down. Yes.
All right, there we go. So as the book was sliding down the ramp, this total force right here, when I add these three forces together, I should get 1.309 newtons, unless Carrie wants to change her mind.
No, sorry.
Presumably, if it had not been that, somebody else would have chimed in, I would hope. So I'm going to add these three forces together. They're not going to add up like in the force table lab where they add up and get back to where they started, or close. These are not. So I'm going to go down. So probably should have started that one higher, but I didn't. So my total force is 1.309 newtons. And so basically, I'm going to be adding, I have weight going down like this. I have normal force going like that. And I have friction coming back that way. That's basically what it's going to look like. My resultant, 1.309 newtons. That's the resultant vector. So we need a scale. And I need the room. There we go. All right. What is the weight? How do I find the weight of this book? Assuming my mass is correct. In unison would be really cool right now. How do you find the weight of an object if you know its mass?
You multiply it by 1.
All right. What formula are you using?
W equals M times G.
Yep. So I know W is equal to mg. There is enough uncertainty in here. I mean, was it exactly 30 degrees or was it 29.9? I mean, there's a whole lot of flexibility there. The timing, we had a spread from, I think, 0.96 to 1.2 seconds. So 9.8 is probably fine for this. So 0.7 kilograms times 9.8 meters per second squared. And we get 6.86 newtons. So whatever scale I'm using, I need to be able to fit 6.86 newtons down this way. Let's see how much space I have. Since the weight goes down the farthest, there's my weight right there, and there's my normal force and my friction. So I have about 66 centimeters to play with. What I'm going to do is I'm going to draw this line a little bit higher, so I have at least 68 centimeters, because I think that'll just make life a little bit simpler for me. All right, so let's go through that exercise again. Is that level?
Mhm.
All right, so I am going to let 1 Newton equal 10 centimeters. There's my scale. And so therefore, when I draw my weight vector here, I need to draw it 68.6 centimeters. So therefore, weight, or 68.6 newtons. Try that again. 6.86 newtons would be 68.6 centimeters.